last two classes, we worked on random number generation, random number sequence generation with either modular arithmetic, where we actually wrote a program to generate random sequences with modular arithmetic, or with bit scrambling, where we discussed modern random number generators that use bit scrambling for random number sequences. And then in the last class, we walked through several topics relevant to physics problem solving that you can solve with random numbers. One was related to statistics, probabilities. Another one was related to numerical integration. And the third was related to calculating basic fundamental natural constants. And all of those could be done with random numbers and random number sequences. Over the next four classes, we're going to walk through four separate topics, and we're going to perform, using random number sequences, Monte Carlo calculations of radioactive decay, Brownian motion, gas laws, and ferromagnetism. I should say that today's class of the radioactive decay, Tuesday's class of the Brownian, next Tuesday's class will be Brownian motion. Thursday's class, I'm not here, I'm away. But I have a spare spot at the end of the semester. So I'm just going to slide all the classes back one class. So I'll have to change the schedule. I'll send you the homework schedule. There'll just be one class next week, but we'll carry on with the same set of classes, just displaced by one. And then so the following week, after next week, we'll carry on with these topics, and we'll do the gas law, we'll do ferromagnetism. I'll send you a Canvas announcement so that you have a reminder that there will be no class next Thursday. Okay. In each of these topics, radioactivity, Brownian motion, gas law, and the last one, magnetism, we're going to generate random numbers with the Mersenne twister in NumP. We're going to generate random floats from 0 to 1 with that Mersenne twister in NumP. So our whole work is based on this one function here, random float. So radioactivity, just a few introductory words about radioactivity, about the importance of radioactivity, the relevance of radioactivity, and so on and so forth. So as you probably know, likely know, radioactivity was discovered more than 100 years ago in minerals, natural minerals, containing uranium and containing thorium. And uranium and thorium are found in rocks, they're found in soil, they're found in the oceans. And they're a source of much of the natural radioactivity. So that was the origins of radioactivity. If you want to think about it this way, the uranium and thorium that are this source of much of the Earth's reactivity, they're the species of unstable radioactive atoms that have the long enough lifetime to be kind of the last survivors of the production of atoms and nuclei in stars, in stellar explosions that the Earth and the solar system is made out of, constructed from. So those thorium atoms, those uranium atoms that are radioactive but are barely radioactive, have very long lifetimes, are these last survivors from the creation of the atoms in stars. So uranium and thorium were kind of the beginnings of what, alchemy has a long history. They're the beginning of modern alchemy, real alchemy, where you can change the form of elements. You can change one element into another element. In the radium, the thorium, for example, change into stable isotopes of lead via radioactive decay chain. So it was the beginning of that. The first artificial creation, sort of human-made creation of radioactivity by nuclear reactions dates back to just before, a little bit before the Second World War, so in 1934. That was the first time that radioactive nuclei were made by humans in nuclear reactions. And we're going to focus a lot of today's class on the decay law for radioactive isotopes. I'm going to walk through various examples of the decay law for radioactive isotopes. It applies to natural radioactive isotopes like the thorium and uranium chain. It applies to man-made, human-made radioactive isotopes. So we're going to be discussing that decay law. And one thing about a decay law, it is kind of the quintessential illustration, quintessential example of the probabilistic character of the quantum world, quantum physics, where only probabilities can be calculated. So that's just a background. Here's an introduction to the decay law. We're going to look at different applications of the decay law. We're going to make Monte Carlo calculations using the decay law. But the basic idea is represented up here. So that equation, you're asked to imagine you've got a sample of radioactive of uppercase N radioactive atoms and nuclei. And the question that's posed by the equation is how many of those atoms or nuclei decay in some period of time. And the decay law in this form, this is in its differential form, is an equation for the number of atoms or nuclei that decay in a certain time interval. So N is our number of atoms decaying, T is our time interval. N, as we mentioned, was the number of atoms or nuclei in the entire collection, the entire ensemble. And lambda is a parameter. It's a rate, call it the decay rate, and it describes the particular atoms or the particular nuclei that decay. So it would describe whether these atoms are highly radioactive and decay with a high rate, or these atoms like uranium and thorium are weakly radioactive and decay with a slow rate. So that's what lambda is, and it's measured in rate. It's measured in units of inverse time. So it's measured in, you would measure the rate in inverse seconds or inverse days or inverse years, depending on whether you've got a highly or weakly radioactive sample. When we think of the equation here, tend to think about the dn and the dt. So that's the number of decays and the time interval for those number of decays. We tend to think of those being either a small fraction of the total number of nuclei or atoms for the dn, or a small interval of time for the dt. But we also tend to think of the dn's and the n's as being large enough that we can think of them as kind of continuous variables, as smooth variables, rather than discrete distinct events of the decay. So that's when we think about the decay law of an equation or a formula, that's how we tend to think about the parameters in the decay law as being smooth functions. But of course, it's describing this probabilistic quantum mechanical event, the decay, and that is not smooth and continuous. Rather, that is distinct decays at unpredictable times. So we should remember that. So this is the differential version of the decay law. This is the integral version of the decay law. So I can get the integral version from the differential form just by basically direct integration of the differential form, because I can separate the variables. I can put dn over n, the dependent variable, on one side. I can put the dt on the other side, and so I can integrate two sides. And if we do that, we get this result here, which is the famous exponential decay law, radioactive decay law. So you see here that the number of samples as a function of time that are surviving, so like the surviving uranium or thorium on Earth, is equal to the original number of uranium or thorium atoms on Earth at Earth's birth, times this exponential factor, which in the exponent has the decay constant of the uranium or the thorium that's dictating how quickly or slowly and the time elapsed since the birth of the Earth or the production of the uranium. Okay, so that's the decay law. Sometimes we use the decay constant to characterize the particular radioactive material. Sometimes we use the inverse of the decay constant. So that's called the lifetime, as units of time, so seconds or days or years. So we'll use a lifetime, here it is tau. And sometimes we even use a half-life. So a half-life is also a time, like the lifetime is a time, that's characterizing how rapidly or slowly the decays occur. The lifetime is the half-life is the time it takes for half of the atoms or nuclei in your sample to decay away. Okay. As I said, we think about that differential form for the decay law, or that integral form for the decay law, as involving these smooth quantities, the number of atoms or molecules and the time evolving smoothly with time. But really, they're statistical fluctuating quantities. And so I just wanted to say something about the fluctuations, how we represent the fluctuations of the number of decays of any particular radioactive atom or nucleus. So on this slide, I'm asking you to imagine that we have a radioactive sample and we measure the decays from the radioactive sample by some sort of instrument for measuring decays of the radioactive sample. And we measure in some time, I called it delta T, some number of decays, I called it lowercase n, and we're going to make that measurement of the number of decays in this time interval. We're going to make that measurement many times. And because of the statistical nature, the probabilistic nature of the radioactive decay, we're going to get different outcomes from our different measurements. We're going to get different values for the number of decays in the same time interval. And so we're going to get a probability distribution of the number of decays in a given time interval. That probability distribution of the number of decays in a given time interval will have a certain average. If we measured it many times, we can calculate the average. It will also have a certain standard deviation that characterizes the amount that it fluctuates from measurement to measurement. We call that, say, the standard deviation of sigma. The Poisson distribution, this equation here, describes the probability of the different outcomes from the measurement of the number of decays in some fixed period delta t. So it's a probability distribution that tells us the probability of getting n decays, where n could be, 10 decays or 9 decays or 11 decays. It will tell us the probability of those possible outcomes. And it tells you the probability of those possible outcomes based on, well, what is the outcome n that you're asking for the probability of. So it's obviously a function of that n. And then it's also a function of the average number of decays that you would get if you made the measurement many times. And that's the m in the equation. So if you look on the right-hand side, the variables that are on the right-hand side are the average number of decays that you would obtain by averaging many measurements. That's the m. And the number of decays that you want the probability for, that's the number lowercase n. So this tells you for a given average number of decays what the probability of any particular number of decays is. So supposing the average number of decays you calculated to be 10, then it would tell you the probability of getting 10. That would be the largest probability. It would tell you the probability of getting 1 less or 1 more, 9 or 11. That would be a somewhat lower probability. It would tell you the probability of getting 2 less or 2 more, 3 less or 3 more. It would tell you all those probabilities described by this this distribution that we call the Poisson distribution. Here it's just plotted in this upstairs plot for several different mean values. So plotted the distribution P of n, the probability of getting n decays for 3 different mean number of decays in the period of time, a mean that is 1. So you made a measurement where on average you got 1. Another measurement where on average you measured 4, and another measurement where on average you measured 10. So if you look at the case of the mean being 1, that's the yellow points. Well, it's about a 35% chance, 36% chance of getting 1 if your mean is 1. There's actually about also a 36% chance of getting 0 if your mean is 1. So you can end up with no decays. And then there's decreasing probabilities of getting 2 decays, about 20%, 3 decays, less than 10%, and so on and so forth. So that's what this yellow distribution describes. And you can see here the distributions for higher values of the mean counts for 4 and for 10 in the magenta and the light blue. As you increase the number of counts, let's say you increase the mean value for the number of counts, the Poisson distribution, which is a asymmetric distribution about the mean, so it's not symmetric about the mean. The curve in yellow is certainly not symmetric about the mean of 1. The magenta curve is also, you can see, not symmetric about the mean of 1. And the blue curve starts to look, it's not quite symmetric, but it's almost symmetric. So the Poisson distribution is not symmetric about the mean, but as the the number of mean counts gets larger and larger and larger, it becomes more and more symmetric about the mean. And it starts to approximate to this equation here, which is the equation for the normal distribution, which is symmetric about it. So this equation is also, like, it's an equation for the probability of getting a certain outcome, a certain number of counts, just like the Poisson. It's an equation that depends on the mean number of counts, and it depends on the number of counts you're asking the probability of obtaining. So this right-hand side here depends on n and m, just like this equation, Poisson equation. N and m hidden in sigma is the square root of this of n down here. So it's dependent on the same n and m. It gives you the probability, but it's just a probability that applies for when m is relatively large. So maybe m is 100 or 1,000 or 10,000. The normal distribution would be a good approximation to the Poisson distribution. The normal distribution is, as I say, a symmetric distribution about the mean value. So here's plots of means of 10, 15, 20, 30, if I walk from the right towards the left here. And these are the normal distributions, Gaussian shaped distributions that appear to be symmetric. So these are the statistical fluctuations, which are kind of hidden behind the decay law, within the decay law. So that decay law applies to radioactive decays, and it applies to sequences of radioactive decays. And this slide, I just put out in our interest that on Earth, there are actually 4 main radioactive decay sequences that account for almost all of Earth's radioactivity, terrestrial radioactivity. They are the thorium series that we had talked about. They are the another series, famous series, is the radium series, and 2 more series. And they're all on this slide here. So the thorium series is actually this one in blue here. And then the other 3 series, there's a radium series, 2 more series are radium series is in red, and then the active 2 other series are in green or in magenta. You see they're all series in which very heavy radioactive, weakly radioactive, very heavy weakly radioactive atoms decay into stable, say, non-radioactive species. So that's the route from the top left to the bottom right is from weakly radioactive to safe and stable over here. So as an example for the thorium series, the starting point, the thorium isotope has a lifetime that is scale of billions of years. So that's the lifetime that's needed to have survived since the birth of the Earth from the product of the stars. So it has that billions of years lifetime. So it's very weakly radioactive, but it ends up turning into lead, ordinary old lead, which is then stable and stable. It does that through a whole sequence of different types of decays. And those decays are decays you've probably heard of, alpha decays, beta decays, and so on. And those decays involve isotopes between the bookends of the thorium and the lead, where those isotopes might have, some of them have lifetimes that are thousands or millions of years. Some of the isotopes have lifetimes that are seconds or fractions of a second. So between the bookends of the very weakly radioactive thorium and the completely stable lead is a range of decays and a range of lifetimes that spans from millions of years through to tiny fractions of a second. So that's all in. On the way, one of the products is radon. Radon's famous because it's a product of the thorium decay, which is in the earth, in the soil, in the ocean. It's also a product of a different radon isotope. It's a product of the radium decay chain. Again, that's in the earth and in the soil and in the ocean. And of course, that's famous because that is a radioactive gas. And that's a radioactive gas that can accumulate in your basement. And that's a radioactive gas that's a significant health hazard. So that's a downside of this legacy of the formation of the atoms and the nuclei, is that this chain involves a radioactive gas that is some sort of danger to us. Yeah.
If you have something like neutrino oscillations, would it be like somewhat similar to this, but with a closed chain, basically, of decays?
Yeah, so we do use, I mean, you use this, what you use the word oscillation rather than decay. So I think obviously both of them involve a transmutation of a species of neutrino or a species of atom or nucleus into another species. And then I just think we use the word when it's a one-way street, right? And you decay and you're not going to go back. And we use oscillation when it's two-way street and you can come back around.
Okay.
Yeah. So I think that's a good point. Yeah. Okay. Well, I don't go through those. I don't know what I put them in there. I did want to write down some formulas now. I wanted to write down some formulas that we will use in today's class and we'll use in the homework assignment for radioactive decay sequences. And so we've kind of talked about an individual decay, and then we just talked about, well, there's actually chains of decay. So let's step through a couple of simple cases. The first one is where you just have a radioactive atom decays to a stable pair. That's kind of like A decays to B. And then we'll talk about the case where you have a radioactive atom that decays to another radioactive atom that decays to a stable descendant. That's like an A to B to C decay sequence, and that's a more complicated sequence. In the A to B sequence, what are the interesting questions about A decaying to B? Well, the interesting questions or the interesting things in measurement are what's the population of A as a function of time? What's the population of the species B as a function of time? And likewise, in the A to B to C, becomes more interesting. What is the population of A and B and C as a function of time? It gets more complicated. And then you could imagine, well, if you've got a whole thorium decay chain, or you've got a radium decay chain that involves many decays through many species, that's a very complicated problem. So I'll just say a few words about that. Okay, so this is the case of radioactive atom A decaying to stable atom B. And what are the populations of the radioactive atom A and the stable atom B as a function of time? And my example is a famous case of A to B decay chain, which is carbon-14. So carbon-14 is used for dating of living things, basically. It tells you when the living thing died. So it's used for dating when the dead living thing was previously alive, and it works on the scale of dating things that were alive up to say 50,000 years ago, that sort of scale. And the reason you can date with carbon-14, why it records the when the living thing died, is because carbon-14 is continually produced in the atmosphere by cosmic radiation. So there's lots of carbon in the atmosphere, carbon dioxide, for example, in the atmosphere, and that, but there is a very small fraction of carbon-14 isotope of stable carbon-12 in the atmosphere that's produced by cosmic radiation that's always impinging on the Earth. So we're breathing in carbon all the time. We're breathing in the stable isotope of carbon-12. We're breathing in this tiny, tiny fraction of carbon-14. And so our bodies, while we're alive, because we're, breathing in, we're living, is, a large component of our body is carbon, and that carbon has a certain fraction of carbon-14, a certain tiny fraction of carbon-14. When I die and I'm no longer breathing, then I'm no longer, the carbon-14 is decaying away. But the carbon-12 is stable. So the proportion of carbon-14 to carbon-12 in my dead body will start to go down because I'm no longer breathing anymore and maintaining this equilibrium. And the longer we wait to measure my carbon-14 to carbon-12 ratio, then the smaller that ratio. And so that ratio becomes a clock or a measurement of when I passed away. So that's how we measure things when living things died up to about 50,000 years ago. The 50,000 years rough number, right? The lifetime of carbon-14 is about 5,000 years. It's like 5,700 years. So one lifetime of carbon-14 is 5,700 years. By 10 lifetimes, so if you wait 10 lifetimes, you'll have almost no carbon-14 left. You'll have no sensitivity to how long ago the living thing died. And so that's why the range is up to, say, 50,000. Okay, although it's too long and they need introduction. But anyway, this is the differential form of the decay law applied to the changing populations of carbon-14, which is A in a notation, and the product, which is stable nitrogen-14, which is the B in a decay chain. So this is just a slightly modified version of the decay law, the differential decay law, that the rate of change of the number of species A is equal to the decay rate times the number of species A you have times the time. And I've just rewritten it as En A over T. The minus sign, of course, is important because it's a downward change. The number of species A atoms, nuclei is decreasing, so that's negative. What about species B? Well, species B is going to be accumulating. When species A decays, species B grows correspondingly. Every A turns into a B in this decay chain here. So as A decreases by minus lambda A and A, then B is its population is going to increase by lambda A and A. So the only difference here is a loss to A is a gain. So these are the two differential equations that describe the two dependent variables, the populations of A and B as a function of time. And think of those as a pair of coupled differential equations. But they're coupled because, NA appears in both of them. So they're not separate differential equations, they're coupled together. But we learned how to solve, first order differential equations and multiple first order differential equations. And we can use our Euler method or Runge-Kutta method just to solve these equations. These ones you can also solve straightforward analytically. So I wrote down the solutions here analytically, but we'll solve it with random numbers, Monte Carlo. We'll solve it with the Euler method and numerical integration. But these are the analytical solutions. And they're kind of the obvious analytical solutions that you would expect. The number of atoms A or carbon-14 is decreasing exponentially with time according to the exponential decay law, this decay constant here, characterizing carbon-14, whereas the number of species B, that's going to be increasing with time. And in these solutions here, I pick a particular pair of solutions that correspond to kind of certain initial conditions. My initial conditions here are actually, which is unrealistic, that they're all, you start with all atom A species at time 0. You're just going to let them decay, and there are no atom B species at time 0. So this solution corresponds to those initial conditions. Okay. This is a next more complicated casing. We've got radioactive species A decays to radioactive species B decays to stable species C. The example I like from this, because I know it well, is that there's a famous case series for fundamental particles, or elementary particles. That is a to B to C sequence. It starts with a particle called the pion. Starts with a charged pion. Pions come in positive and negative species, positive and negatively charged species. The pion decays to another unstable subatomic species. It's the muon. The muon also comes in positive and negatively charged versions. That decay is accompanied by the neutrinos that we just talked about. So each decay of a pion produces a muon and a neutrino. Then the muon itself decays to, we think of a muon as we call it often a heavy electron, because it's like an electron, except it's just a much more massive, 200 times more massive electron. It decays to an electron. Other than the mass, 200 times the mass of an electron, it has the same properties as an electron. So it is like heavy electron. So that's the decay sequence. These were the original, you can now buy these as artwork. They're original actual photographs of the first observations of the decay sequence, where you get a track from a pion, then at an angle from it, a track from the decay muon, and then a track from the electron. When the pion decayed to the muon, it produced a neutrino. You don't see it in the photograph. You only see charged particles in the photograph. When the muon decayed to an electron, it also produced a neutrino and an antineutrino. You don't see the neutrinos in the photograph again. You only see the charged particles. So you get this funny series of kinks, which, from some sort of detective work, were eventually figured out to be a pion decaying to muon decaying to electron, with the emission of neutrinos accompanying each of the decays, and the decay occurs through the weak form. Anyway, this is kind of a classic A to B to C, where A is the pion, unstable, B is the muon, unstable, C is the electron, stable. Okay, so we could construct the decay law for this A to B to C decay chain. We can write down the differential decay form of the decay law, and then we can solve solve it for the number of each species, say the number of pions, muons, and electrons as a function of time. And we can, again, in this case, you can do this analytically, find the solutions of A, B, and C as a function of time. And we're going to do it, or we're going to do it numerically with a random number sequence, Monte Carlo method, and we're also do it numerically by solving the ordinary differential equation using Euler or Runge-Kutta method. We can do all of it. So just like the A to B sequence, the A to B to C sequence, we can write down the equations describing it based on that differential form of the radioactive form. So the rate of change of the number of species A, pions, is equal to, is determined by the product of how many pions there are at the moment in time, and the decay rate of the pion, that's the lambda A. So that's how the pions, the number of pions, is decreasing as a function of time due to their instability. And that's a decrease in the number of pions, and so there's the minus sign. When the pion decays, it decays into a muon. So a loss of pions corresponds to a growth in the number of muons. So whenever we lose a pion, which is characterized by minus lambda A Na, we're going to gain a muon characterized by plus lambda A Na. So we get this term. This is the growth of the number of muons due to the decrease in the number of pions. But muons themselves are unstable. So the muons themselves will be decaying, and they'll be decaying with this second term. This corresponds to the loss in the number, and that's just the given by the number of muons you have in your current population times the muon decay rate. So that's the lambda B. So that causes a loss in the number. And finally, if you lose a muon, well, you're going to gain an electron, because the muon is decayed to an electron. So the rate of change of the number of electrons in your population, well, that grows as the muons decay. So any loss of a muon in this amount controlled by lambda B and B is a gain in the number of electrons. So it's this plus lambda B. So that's easy to kind of construct the differential decay equations for the sequence A to B to C. So starting with the differential equations, it's easy to write down the changing populations of A and B in an A to B sequence. It's easy to write down changing populations of A, B, and C in an A to B to C sequence. And then you can go worry about solving the differential equation for A to B for the populations as a function of time, or solving the differential equation for A to B to C for the populations as a function. I wrote down here the solutions to these equations. This gets harder to solve analytically. The only way I know how to solve this analytically is trial and error. So, and a trial and error solution to this problem would be to say, well, look, I'm expecting exponential functions in my solution. Got an exponential decay law. I'm going to expect exponential functions in my solution. I've got two decay constants that control the rate of the exponential decays. And so I'm just going to hypothesize a solution that contains exponentials like e to the minus lambda at and e to the minus lambda bt, because that's really the only variables I got to work. So if you make a trial and error solution that has that form, has an exponential term e to the minus lambda at, has an exponential term e to the minus lambda b2 bt, and then match that general equation, that trial and error solution, to your initial condition. the initial conditions might be, the case I picked here was that I start out with all pions at time 0, and I have no muons, no electrons at time 0. I mean, with those initial conditions, you can match your exponential solution to the initial conditions, and this is what you want. So you get the number of pions is decaying away with a pion lifetime. The number of muons and the number of electrons, how they grow, how the number of muons grows and falls, because it's going to grow and fall, because it's being fed and it's feeding and it's also being lost. And how the number of electrons grow is ultimately just going to grow through this decay sequence. How they grow depends on both time constants of both decays. So these the time constants for the population of the muons and the time constants and the description of the population of the electrons is now much more complicated in just this A to B to C sequence. It becomes a much more complicated problem in how these populations of muons and electrons evolve as a function of time. I won't go into much detail of that, but there are two kind of extremes that you could imagine. And the pi mu e decay is actually kind of one of those extremes, because it's the pion decay is 26 nanosecond lifetime short. The muon decay is 2,200 nanosecond lifetime, so much longer, 100 times longer. So that's a decay where the lifetime of the pion is short, high decay rate. The lifetime of the muon is long and low decay. So that's kind of one extreme. Lambda A is much bigger than lambda B in the pi mu e decay sequence. When you have that situation, effectively the pions decays occur quickly. They kind of gush into, think of it like a fluid, they gush into the muons, and they quickly become, the pions quickly turn into muons. And then what you see in the time distribution of the muons and the electrons is just the decay of the muons with the muon decay rate, and the growth of the electrons with the muon decay rate. So in this extreme, where the pions decay quickly and essentially quickly vanish from the problem, what you're left with after that early transient is basically a collection of muons that are decaying away with the muon lifetime, and a growing number of electrons that are accumulating with the muon. So it becomes a sort of simply understood picture of what's going on. The other extreme, that's the extreme here, is when the parent lifetime is slow, and much slower than the A's lifetime is much slower than B's lifetime. So that's the other extreme. That would be like the pions having a lifetime of 2,200 nanoseconds. The muons have a lifetime of 26 nanoseconds, which is not the case. If that happens, it's like the long-lived initial state A kind of slowly trickles into the short-lived state B. And then the short-lived state B quickly decays away to the stable species C. And in that situation, where the first decay rate is a gradual trickle, and then the second decay rate is the gush into the final stable species, you get a very interesting situation where you kind of get an equilibrium number of the species B. It's just a balance, an equilibrium between the trickling in and the rushing out causes kind of a constant, stable, steady population of the species B with its short lifetime. It's always being trickled into by species A, which is maintaining the population. But then it's always quickly decaying away species C. So you get this sort of length. It's a way of, if you've got a short radioactive species and you want to, for example, for medical applications, make it deliver its radiation over a longer period of time, you want this mother or parent that has a long lifetime. You supply that, you let it decay into this child or daughter that has a short lifetime. And the population of the daughter, the child, is maintained by the long-lived parent or mother. Okay. This is if you've got multiple decays. I'm not going to go into that, but I thought I wanted to put it in there. Okay, let's get on to Monte Carlo simulation of this. Let's say this is simulating radioactive decays. It's a nice example of Monte Carlos. It's a nice example of computer simulations that are using random numbers to simulate this decay. These Monte Carlos that we're going to talk about in this radioactive decay example are these Monte Carlos are used in physics, they use chemistry, they use biology, medicine, engineering, economics, everything. They're like little randomized experiments. Monte Carlos are like little randomized experiments involving sets of random numbers, sequences of random numbers. The earliest random Monte Carlo simulation was one done by hand, not done by computer. But an early version of a Monte Carlo is, if you look at the floor tiles here, right? They're spaced apart by, I guess, 12 inches or whatever. So supposing I get a bunch of knitting needles from home, they're about 12 inches or so long, about same sort of stacker. If I threw them on the floor, that I would be conducting a Monte Carlo calculation in which I can calculate the value of pi. I could calculate how many of the needles, if I just throw them randomly on the floor, cross one of the lines between the tiles versus how many don't. That that fraction of needles that cross tiles boundaries compared to the total number of needles that I threw on the floor, that fraction is determined by geometry, is determined by involves time. And so a Monte Carlo calculation of pi would be throwing the needles on the floor, calculating how many cross, how many don't cross the tiles. From that, I can derive a value. And the statistics on that derivation of a value for pi would depend on how many knitting needles I threw. And of course, I could do an equivalent to that on a computer, and we did an equivalent to that on a computer in the last class. Another famous example of the beginning of computer-based Monte Carlo simulations using random number generation was for the Manhattan Project. One thing that was needed for the Manhattan Project was understanding of the diffusion of neutrons produced in nuclear reactions through materials. So a problem like diffusion of, if you drop some dye in some water, right? That dye will diffuse away from the point where you dropped it. This is like you produce some neutrons in some material that diffuse away from that point. They needed to understand that diffusion. Well, they used first computer use of Monte Carlo simulations was to calculate that diffusion by a Monte Carlo method, and we're going to look at that basically in the next class, in Tuesday's class. But anyway, we're going to apply here the Monte Carlo method to radioactive decay. So I think I'm just going to go to the code. I think I was planning to go to the code half an hour ago, but just didn't stop rattling on about radioactivity, but here it is. In this code, I'm going to numerically solve the radioactive decay law correspond to a pion decaying to a muon. So that's an A to B sequence. In the corresponding homework assignment, you're going to extend this code to solve the problem of the decay of the pion to the muon, which decays to the electron. So the A to B to C decay sequence we just talked about. But the way we solve using Monte Carlo, the A to B sequence, is the way you'll extend it to solve the A to B to C. I've not only, though, in this code, solved the problem by a Monte Carlo method by generating random numbers, but I've also solved it by, this would be like nostalgia for us, using solutions to ordinary differential equations. I used Euler method to solve the ordinary differential equations as a point of comparison. The interesting thing about that comparison is you use a Monte Carlo method. Well, you actually, not only do you simulate the growth or decay of the populations, but you simulate the probabilistic statistics involved in the radioactive decay. If you do the ordinary differential equation numerical solution, you solve for the growth or the decay of the populations, but you don't pick up the quantum mechanical probabilistic nature. Okay. This is just me setting up in this cell the parameters of the problem. As I say, I'm going to just concentrate on A to B decay where pions decay to muons, and I'm going to think about that special initial case where we only had pions and we had no muons. So I'm picking 1,000 pions and 0 muons at time 0. I need the lifetime or the decay constant of the pion. I said that the pion lifetime was 26 nanoseconds. That's the number I remember. I don't remember the decay constant, so that's the number I worked with. So this is 26 nanoseconds. Then I've got to define I'm going to define a discrete time. That's kind of my world for what the decay's decayed in. It's this discretized version of continuous time, the real world. I'm going to pick time intervals, time increments or ticks of the clock of 1 nanosecond in length. And I'm going to pick 200 nanoseconds duration for my discrete time, because my lifetime in muon is 26 nanoseconds. So there'll be essentially none left after 200 nanoseconds. We compare to the,
real quick, isn't that supposed to be plus lambda 1 times n?
Oh, yeah. You're absolutely right. It should be pluses. Thank you. Yeah, that's very important. I put these two functions in here. Obviously, I just copied these from, I don't know, my harmonic oscillator or my falling body differential equation solutions, and just modified the differential equation for my particular system here. Remember, in this A to B decay sequence, we're interested in populations of A and B. Both of them are described by differential equations. We wrote those differential equations down. Those are two coupled differential equations, and they're written out this in this function here. So this is the fact that species A, the rate of change of species A is the population of species A at that moment in time times the decay constant, or divided by the lifetime, using the language of lifetime. And the myosine, as you pointed out, that's the fact that this species is decaying away. Its number's going down. The population of species B, that's the second differential equation. Rate of change of population B is in proportion to the the population of A. It's not the population of B here, it's the population of A, because that's the one that's causing the change. Doesn't care about B zero. So this is the population B at the current moment, again, times the decay rate of, so this population A at the current moment times the decay rate of A. I'm using the language of Weidner. And as you say, minus and plus, because one's decay, one's growth. Okay, this cell here, I'm going to just quickly glance over it because it's, again, it's just the Euler method for solving the problem. I set up a function that contains the differential equation. I've set up a function that contains the Euler method. I'm going to just define my proxies for continuous time, this discrete time, initialize my proxies for the dependent variable. The dependent variable is a kind of meta variable again, where we've got, it's a 2 by n matrix because one of the columns of this meta variable is the populations of species A, the pions. The other is a column of populations of species B, the muon. So that's the meta variable here. I know the initial state for the pions and muons. There was 1,000 pions, there's no muon. So I set the initial conditions here for the meta variable, and then I calculate with this loop here over all the time increments in my discrete time. I calculate the future population from the current population. So yj, this is the variable that's containing the current population of pions and muons, and it's calculating the future and the next time populations of pions and muons. And then we just walk around that loop, calculating for every current value of the populations, the future values, and in that way reconstruct out of the initial conditions and the decay laws the populations of pions and muons. And then I just stripped off the pions and muons populations into these two variables, M1 and M2, with some slicing, and I plotted them. Yeah, down here. And this is kind of what we expect, I think. Magenta is the pions, and red is the muons. We started at time 0 on the horizontal axis with 1,000 pions and 0 muons. So that's right. The pions decay away, they are decaying away, and their lifetime is 26 nanoseconds. In 26 nanoseconds, we expect roughly 2/3 of the pions to have vanished. The muons, on the other hand, every loss to the pion family is a gain to the muon family. And so the muons are growing exponentially, and we end up with, at late times, the reverse populations. Right now we've got 1,000 muons, and we've got 0 pions if we went any lifetimes out. So that's how we could construct the numerical solutions of the differential equations. But now let's look at the Monte Carlo. So this is really the new part. You don't need to see the plotting. So my Monte Carlo calculation of the pi mu decay sequence and the determination of the populations of pions and muons as a function of time with all the statistical, probabilistic, quantum mechanical fluctuations of pions and muons as a function of time. It's just based on these few lines of code. So it's a straightforward calculation. And in solving the homework back A to B to C rather than A to just B, you may want to just extend this to be A to B to C from A to B. So first two lines are just, again, me, for some reason, because I wanted to compare things, I think I made a fresh time variable and I made a fresh meta variable for the dependent variable, which contains both the population of muons and population of clients. So that's what I've done up here. This is going to be a very important number to me. So imagine this time evolving from time 0 to 200 nanoseconds. And the way it evolves is not smoothly, but in these ticks: 1 nanosecond, 2 nanoseconds, 3 nanoseconds, 4 nanoseconds. In these increments, 200 increments of 1 nanosecond. The important number that I'm calculating here is, what is the chance of a pion became to a individual pion became to a muon in that 1 nanosecond? The chance of a pion became to a muon in that 1 nanosecond is the product of that time interval of 1 nanosecond, so delta t, times the decay rate of the pion, or I can't remember the decay rate of the pion, but I remember the lifetime, divided by the lifetime. So this probability here, it's going to be a small number, right, is the time interval, 1 nanosecond, divided by the pion's lifetime, 26 nanoseconds. So it's roughly 0.0, something like that. So that's the chance. Yeah, so if I'm watching any one of my 1,000 pions, that's the chance of watching pion number 1. It's the chance that it decays in the next one nanosecond, about 0.04. And I'm going to keep using that number, because what I'm going to be doing is something that is the most simple thing I could think of doing. I'm going to look at every pion during that first nanosecond, and I'm just going to ask the question, did it decay? Based on this chance, did it decay? Now, I'm going to look at the first one, and I'm going to look at the next one, and I'm going to look at the next one, and I'm just going to count up how many did decay. So let's see how that works. I've got nested loops here. I've got one outer loop over the time, which is the independent version. This outer loop with index IT, with counter IT, is just counting through all those 200 ticks that are in the complete time interval that I'm watching the two populations. So that's the outer loop. And as soon as in that outer loop, I initialize the number of pions, NP, at that time, the number of muons at that time, to be n pi and n mu. So n pi and n mu, where you remember we set those to be 1,000 for the number of pions, and 0 for the number of muons. So the first time I go in this loop, when IT is 0, I'm going to set these variables to be 1,000 and 0. But later on in the loop, I'm going to be changing them. See down here, later on I change them. And so the next time I go around the loop, these numbers will be slightly different. This one, the number of pions will have decreased, and this one, the number of muons will have increased because of the decays, and I'm accounting for that here. I set the current values of the numbers of pions and muons here. And this is ultimately the solution to the problem that I'm going to build up. I'm going to build up this array. Okay, so we're in the loop, and we're in the loop at a particular number, at a particular time. And what I really want to calculate is how many decays occur in that particular 1 nanosecond. So to do that, I'm going to walk through all the pions that I've got. When I first go in the loop, this number of pions will be the original 1,000 pions, right? But the second time I go in the loop, it might be a little less, because maybe a few pions have decayed. And the third time we go around the loop, it'll be a little less still, because more pions have decayed. So For each time interval, this range of how many pions I'm going to look at, ask if they decay, is going to go down and down and down and down as the pions are disappearing. For each pion, I ask this question. This is a yes or no question, a true or false question. That's going to tell me whether the pion decayed or the pion didn't decay. I'm going to generate a random number. I generate a random flow that goes from 0 to 1. I'm going to ask the question, is that random number less than that probability that I calculated? The probability of a pion decaying in one clock tick. Remember that was a small number. So if that number is less than that random number, is less than that small number, that the decay happened. If that random number is bigger than that probability, a small number, then the decay didn't happen. Look, most of the time, my random number from 0 to 1 will be bigger than the probability, but occasionally it'll be smaller than the probability of about 0 to 4. If it is smaller, that is a decay, and I increment a counter for the number of decays. I just say I've got a decay. And then I go back around and ask for the next pion, the next pion, the next pion. Once I come out of this loop, this nested for loop here, which is loop over the pions, I've determined how many pions decayed in that clock tick. That at that point I can decrement the total number of pions by that number, and I can increment the number of muons by that number. And I've got a new population of muons and pions to store upstairs. Okay, so that's the idea. It's a rather simple scheme, right? I just walk around for every time interval, and every pion, I just ask, did it decay? I just keep asking this, did you decay or not? Question. I'm going to be asking it tens, hundreds of thousands of times. That's the cost of this method. This is expensive in generating random numbers and asking the same repetitive question. So as a pro to this method, simple algorithm compared to numerical ODE solution, simple approach, but it's a computer expensive in terms of time, random numbers, and you know, nested for loops. But let's just run it. And here's the plot I made of the results. It's the same axes as before. Time horizontally, population of pions and muons vertically. I didn't pick red colors. You can see the two curves, but there's curves and there's points. The points are my Monte Carlo result. So that's discrete numbers of pions and muon populations at each time interval. The smooth curves are my numerical integration of the ordinary differential equation result. That's what I calculated in the last cell. So I am comparing those two things. So when you see these magenta dots, that's my new Monte Carlo calculation of the number of pions, and that exhibits, you know, the decay, but it also exhibits statistical fluctuations. So it resembles nature, and then it incorporates the statistical fluctuations. The ODE didn't do that. The number of muons in green here, the dots, is the growing number of muons. Again, it follows the smooth curve from the solution of the ODE, but it incorporates the statistical fluctuations arising from quantum mechanics. It incorporates that in the solution. So you see the similarities and the differences in these two approaches to the problem. As one more plot I made, I don't need to describe the plotting algorithm, but the top plot is for each clock tick. Vertically, I'm plotting the change in the number of pions. In the bottom plot, For each clock tick, I'm plotting the change in the number of muons. So for any clock tick, the decrease in the number of pions must be an increase in the number of muons. So these are opposite, these plots are mirrors of one another, or opposites of one another. On each plot, I've got a fluctuating set of data points. That's my Monte Carlo result from my Monte Carlo simulation and my random number sequences. And then I've got a smooth magenta curve. That's my ordinary differential equation, numerical Euler method result. So you see again the pion lifetime in the fact that the rate of the decays falls off with time, 26 nanosecond lifetime, according to the pion lifetime, and the loss of pions and the gain of muons. And you see we're reproducing the fluctuations in the Monte Carlo, just a smooth trend in the numerical ordinary differential equation solution.